Seventh grade lesson 12.3 is experimental probability of compound events. We have done experimental probability of simple events, so now we're just going to look at that in terms of compound events. A compound event just means that more than one item is happening when it comes to probability. So maybe I'm flipping a coin and then I'm also rolling a die. So you have two pieces that are being put together. So let's go ahead and use this explore activity to kind of hone in our thoughts, our ideas on how compound probability works. So we have the example again of flipping a coin and rolling a cube dice. And what are the possible outcomes of flipping the coin? What can possibly happen if we flip it and it will either land as heads or tails, right? So we'll put that down, heads or tails. There's two possibilities only. I need to neaten that up. And what about the possibilities of rolling a standard cube, a die? What are the possibilities? I can land on 1, it could land on 2, 3, 4, it can land on 5, or it can land on 6. So there's a total of 6 different possibilities. So if you compound those together, if you put those two simple events together and you say, okay, what are my chances of rolling heads and rolling a 1? And then rolling heads and rolling a 2. So we have rolling heads and rolling a 1. Not rolling, but flipping heads and rolling a 1. Flipping heads and rolling a 2. And we're just going to go ahead and fill this out. Heads 3, heads 4. I flip heads, roll a 5. I flip heads, roll a 6. Those are all of the possibilities where you would flip heads and then roll the dice 1, 2, 3, 4, 5, 6. The other possibilities, I could flip tails and roll a 1. Flip tails and roll a 2. Tails 3, tails 4, tails 5, tails 6. There's a total of how many possible outcomes? Well, there was the 6 here and the 6 here. 6 times 2, right, is 12 possible outcomes for this compound event. That's what they mean by that. And so they give this experiment, and you can go ahead and do this if you want. You can pause the video and do this. They say, flip a coin and roll a number cube. Do that 50 times. Mark in here what you rolled and what you had. Do tally marks for each time you do the experiment. And then tally it out, and then we'll go through the rest of it. So if you do it, your numbers will be similar but different from mine. I'm going to go ahead and do it and fill in the numbers. And then we can compare them, or you can, if you didn't do it, you can just look at mine. Okay, so I have done my experiment. This was my outcome, all of them. They asked me, based on your data, which compound event had the greatest experimental probability, and what was it? Well, it looks like the tails and the 3 came up the most often. It was 6 times out of the 50 times that I tried. If that's a reducible fraction, go ahead and reduce it down. 2 divides into both of those. So my experimental probability, experimental meaning I did the experiment, this is the probability I have from that. My experimental probability is 3 out of 25. Yours would be a little different if you did yours, right? Just find the one that showed up most to answer this question, and that's your numerator. Your denominator is the 50 times you conducted the experiment, and reduce it. And that's your experimental probability. Is it going to end up the same? This question asks, is it going to end up the same next time? No, probably not. First of all, it's probability. Second of all, 50 times is going to give me a little bit of an idea of what the probabilities are, but it's not enough time to get a really solid answer for what probabilities would be. We know it's going to, if we kept going, we know it would start like really balancing out equally across there. Already it was kind of equal for the most part anyway. So I'm just going to put down here, we just don't have enough. We would need to do this experiment more times in order to get more accurate. So I just put down more flip/rolls would be more accurate. So how do I calculate experimental probability of compound events? Well, we're just still doing the division. That result, whatever you got in your experiment, gets divided by the total amount of trials you did in your experiment. So we have a food trailer that serves chicken and records the order size, either 2-piece or 3-piece, and what sides they got on their order as shown in the table. What's the experimental probability that the next order is for 3 pieces of coleslaw? So we're looking for some sort of a fractional answer like, well, there's a 1 in 6 chance or there's a 1 in 5 chance that that's going to be the next order, okay? So here's all the previous, or all of the orders, and they're going to predict based on that what the next order potentially could be. What's the probability that it will be a 3-piece coleslaw? So we're first going to look at what was the experimental probability that we had 3-piece coleslaw. What was that result? That result is 55. Oops, that's not a good color for that. 55. And we're going to divide that by how many total sales have happened already. So you have to add all of these together and thank them for doing that for us. 33 plus 22 plus 52 plus 35 plus 13 plus 55 plus 65 plus 55, and it equals 330. Find the number order. We already did that. Find the number of 3 pieces with coleslaw. There it is. The experimental probability 3-piece plus coleslaw is the number of 3-piece plus coleslaw divided by total number of orders. And then you can just reduce that fraction, 55 330th. You can reduce that fraction rather than divide it because probability can be stated in fraction form. So there's a 1/6 chance that the next order will come out as a 3-piece with coleslaw. That is experimental probability with compound more than one simple event. Finally, just like in when we were talking about simple events, sometimes it's not feasible or not a good idea to get out and do the experiment in real time, real life. So you can use simulations to represent and to make a prediction about what may happen, what may be the next item, what probability of the next item would be. Here's an example of using a simulation for that. So remember in the previous lesson, they were using cards, flipping over cards to make their simulation of an experiment. This one is if you're at a street intersection, a vehicle is classified as either a car or a truck, one of the two, right? And it can turn left, right, or go straight, 3 options of what those things can do. About an equal number of cars and trucks go through the intersection and turn in each direction. Use the simulation to find the experimental probability that the next vehicle will be a car that turns right. So we have something that has 2 possibilities. So what sort of random thing can we use that gives us 2 possibilities? A coin toss. We can make heads represent cars and tails represent trucks. Then the second item is will that item, either the car or the truck, turn left, right, or go straight? So something that can simulate 3 possibilities, left, right, or straight. And they said, well, we could use a spinner divided into 3 equal sectors to represent the 3 directions, left, right, and straight. So they're simulating this with a coin toss and a spin. Find the sample space for the compound events. There are 6 possible outcomes. Cars left, cars right, cars straight, or trucks left, trucks right, trucks straight. So we would perform the simulation using a coin toss for cars or truck and the spinner for left or right. And let's say we went ahead and performed the experiment over and over again, and we recorded our results here. They want us to find the experimental probability that a car turns right. So now we have our experiment already completed. We're looking for car that turns right. There are 6 out of all of them added together, and if you add them all together, apparently it is 50, and you can reduce that fraction down 3/25. So based on this simulation, the experimental probability is 3/25 that the next vehicle will be a car that turns right. The reflect question asks us, predict the number of cars that turn right out of 100 vehicles that enter the intersection. Well, if I go back to this, it was 6 out of 50 cars that turned right, 6 out of 50. What if I performed that 100 times if that prediction were going to give us a somewhat accurate idea? Well, if I multiply 50 by 2, it gets 100. So we're just going to do the same to the 6. 6 times 2 is 12. So I would predict a 12 out of 100, or we can reduce that. And of course, because it's equivalent fraction, when you reduce that, it's going to take you right back down to 3/25 of a chance probability, because they're all equivalent fractions, right? So that is the lesson. That's what they're showing us. So we're just going to play a little bit with that in the guided and independent practice. Be sure to review back if you need to, but I think you'll be just fine.